Okay, the last part of this chapter is on Le Chatelier's principle. And this principle says that when we have a system at equilibrium, that if we have a system at equilibrium, it's happy, it wants to stay there. So if we apply any stress to that system is going to shift either to the reactant or the product side in order to undo that stress and return it back to its equilibrium position. All right, now these stresses could be changes in concentration. These could be changes in volume. These could be changes in temperature. Or this could be the addition of a catalyst. And we'll look at each one of these. Okay, there's nothing in front of that term. All right, so we're going to start out with a reaction, and let's say that our system is at equilibrium, and I'm going to add, let's say, some hydrogen. Okay, so hydrogen is this term. So I'm going to be adding more reactant. So if I add more reactant, my reaction says, oh no, that's too much. I need to get rid of it. So in order to remove some of that hydrogen, it has to go forward, because anytime that I go forward, I use up these things, use up those, and I make more NH3. If the reaction goes backwards, then I am using up this stuff and I am making more of this stuff. Alright, so if I added a whole bunch of hydrogen, I need to get rid of it. In other words, I need to use it up. So if I add hydrogen, it's going to shift to the right. In other words, the forward reaction. In other words, to use up the hydrogen. Okay, since I added some to it, it wants to use it up so it can go back to the way it was. Let's say that I'm going to remove some nitrogen. Okay, so if I take the nitrogen away, the reaction says, oh no, I want the nitrogen back. So if I'm going to be able to make more nitrogen, I have to shift to the left. All right, let's say that I am going to add NH3. Okay, so if I add more NH3, the reaction says, oh no, I don't want that stuff. I want to get rid of it. So if I dump in more NH3, it needs to use it up. So it needs to shift to the left in order to use up the NH3. Okay, so we are always doing the opposite. If I added hydrogen, it wants to use it up. if I take something away, it wants to make more. And if I add something, once again, it wants to use it up. So it's going to shift in the direction in order to do the opposite of whatever it is you're doing. Okay, then we're going to look at changes in volume. Okay, this is only going to affect gases. So we aren't going to be concerned with anything else except for the gases in our system. And what we need to be looking at is that anytime we change the volume, it's actually changing the pressure. So if you decrease your volume, that means the pressure would increase. Or likewise, if you increase the volume, then your pressure would decrease. Okay, and it's all being concerned with the pressure that's happening in my reaction. Okay, so let's say that this is my container and I'm going to increase the volume. Okay, so if I increase the volume, that means that the pressure is going to decrease. And my reaction says, oh no, I want the pressure to go back up. Okay, so on this side of the equation, I have 2 moles of gas, 1 plus 1. On this side, I have 2 moles of gas. Okay, so it doesn't matter which side I shift to because it's going to be the same. So in this case, nothing's going to happen because they both have the same number of moles. So neither side is going to be favored. Okay, well now look at this one. This side has 3 plus 1, 4 moles of gas. This side has 2 moles. Now, if you have terms that aren't gases, you don't count those as the moles. You only look at the moles of gas. Alright, so once again, I'm going to increase my volume, which means I'm going to decrease the pressure. And the reaction says, no, no, I don't like this. Okay, the pressure's too low. I need the pressure to go up. So my options are going to be either making 2 moles or going the other way and making 4 moles. Now if I make 4 moles, that means more stuff in the flask. And if I have more stuff in there, that's going to create more pressure. If I have less stuff in there, then that's going to make less pressure. Okay, since my pressure went down, it says, oh no, I want the pressure to go up. So I'm going to have to shift to the left. This is the side with more moles of gas to increase my pressure. Okay, once again, I decrease the pressure, it wants to increase it and make it go back up. So to do that, I want to shift to the side with more moles of gas. Alright, so anytime I increase the volume, which means the pressure decreases, I want to shift to the side with more moles of gas. Okay, if you do the opposite, then you would shift to the side with fewer moles of gas. Okay, next one, changes in temperature. Now in this case, I'm going to have to be given a reaction that heat is involved. Okay, so let's say that I am going to increase the temperature. The reaction says, oh no, that's too hot. I need to cool off. So this side makes heat, makes it hotter. This side doesn't have heat, so that makes it cooler. So if I were going to increase the temperature, it would want to shift right, which is away from the heat, to reduce the temperature. Okay, I increased it, it wants to decrease it. And in order to do that, it has to shift to the side that doesn't have the heat. If it were to go this way, that would just make more heat. Now, if my heat were on the opposite side, it would make a difference in the side that it shifted, but it still would shift away from the heat if I had increased the temperature. Okay, so this part, shifting left or right, depends, that is determined by which side the heat's on. But if you increase the temperature, it always shifts away from the heat. If you decrease the temperature, it's always going to shift toward the heat. Okay, this particular reaction is endothermic because the heat is on the reactant side. Alright, and my last one is the addition of a catalyst. Now, if I add a catalyst, that makes the reaction go faster. Not only does the forward reaction go faster, but the reverse reaction goes faster as well. So in the end, nothing happens. The reaction goes faster, but it does not change the equilibrium. Okay, it just gets there faster, but it's not going to shift one way or the other one. Alright, let's do an example. Alright, we're going to do all three things, change all kinds of things. Okay, so first, let's add some NO. Alright, so if I add NO, the reaction says, nope, I don't want it. I need to get rid of the NO. Okay, so if I go to the right, I'm making more of this stuff, and I don't want to make more. If I go left, I'm going to use up this stuff. So shift left in order to use up the NO. Alright, let's say that I'm going to decrease the temperature. Reaction says, oh no, I don't like that, it's too cold. I want things to be warmer. So in order for it to be warmer, I'm going to have to shift to the side with the heat. So shift left, the side with heat, in order to heat it up. Let's say for C that we are going to decrease the volume, which means we're going to increase the pressure. Alright, so I need to look at gas. So I have 2 moles on this side, and I have 2 plus 1, 3 moles of gas on this side. So if I increase the pressure is too high now. It needs to decrease the pressure. So I need to shift to the side with fewer moles of gas. So shift left. This is the side with fewer moles of gas. And I believe that there is a table in your book that has all of this stuff kind of in a chart, and it lists like if you add a reactant, which side it's going to shift to, if you add a product, if you decrease a reactant, if you increase or decrease the temperature, and it has all of that summarized up on a chart in your textbook to kind of help you out.